In the last couple videos, we talked about a few schemes to solve the advection equation, which is ut plus aux equals 0. And we concluded that the scheme where we have forward Euler in time, ujn plus 1 minus ujn divided by delta t, right? This is plus a uj plus 1m minus uj minus 1n over 2h is equal to 0. This is not stable. However, both the Friedrichs and Wendroff scheme, they can be considered as designing a scheme for the modified equation, which is, that's what we have now, right? We move AUX to the right hand side, UT is equal to negative AUX, and if we add epsilon times UXX, right, for a small epsilon. This is so-called modified equation. Okay, modified equation. And we're going to do, so we do what we did above. So we're going to do ujn plus 1 minus ujn divided by delta t. This is negative a times the centered scheme, uj plus 1n minus uj minus 1n divided by 2h. And we're going to add epsilon. Okay, what is uxx? That's h squared uj plus 1m minus 2 ujn plus uj minus 1n. Okay, this can be stable. We're adding some artificial viscosity, which is introduce some diffusion to the scheme, which brings in stability. Basically, for the Wendroff, we know that the epsilon LF, this is 1/2 h squared over delta t, and the Wendroff epsilon is equal to 1/2 a squared delta t. It is pretty easy to see that the epsilon Wendroff is actually 1, which is a squared delta t. This is a delta t over h squared times 1/2 h squared delta t. Okay, so cancel h squared, cancel delta t squared. 1 delta t, you get 1/2 a squared delta t. So what is this? This is just a delta t over h squared times epsilon h squared over delta t. That's Friedrichs. Okay, so this is less than or equal to epsilon LF if a delta t over h is less than 1, less than or equal to 1. This shows that the Friedrichs is more dissipative because it introduces more diffusion. Okay, and in this video we're going to work out the stability of these two schemes. Basically, what we're going to do is we're going to write this in terms of uj plus 1. Okay, this is ujn, alright, minus a multiplied delta t divided by 2h, uj plus 1m minus uj minus 1n. The red part becomes epsilon delta t over h squared. Okay, uj plus 1n minus 2ujn plus uj minus 1n. Right, so we're going to have ut is equal to like a u, okay? So which means our ujn plus 1 is equal to ujn plus delta t times a un, a epsilon un, okay? So this is part of this epsilon is what we did already. So this is a epsilon is going to be that negative a over 2h, okay? And we're going to have this matrix we analyzed already. In particular, it's asymmetric, so its eigenvalues are purely imaginary, which means the fourth scheme is not stable. All right, that's what we did already. Now what we're adding is this add epsilon of h squared, the standard guy which we dealt with when we started the elliptic equation, negative, 1, 1, 1, 1. Okay, this matrix. So we're starting its eigenvalues, which is what are the eigenvalues of this matrix A epsilon? We use this exact same technique. So we're going to take V of x to be equal to e to the I 2 pi px, okay? And think, okay, what is ax v is equal to lambda v, all right? And it's pretty easy to see that a epsilon v is j's component, which is going to be equal to this negative a over 2h. We have e to the I 2 pi p j plus 1, x j plus 1, all right? So that's j plus 1h minus, this is the same as we did about 2 videos ago. This is I times 2p pi j minus 1h, okay? And then we're going to get epsilon over h squared, e to the I 2 pi p j plus 1h minus 2e I 2 pi p jh plus e I 2 pi p j minus 1h. Each of these we dealt with before already, okay? So what is this? This is just negative a over 2 pi. ei, we can factor out this same constant, which is ei 2 pi p jh, okay? What we have left is e to the I 2 pi ph minus e to the negative I 2 pi ph, all right? This whole thing. Plus next time we can also factor out e to the I 2 pi p jh. Then we have e to the I 2 pi ph minus 2 plus e to the I negative I 2 pi ph. Okay? So this is just nothing but negative a over 2 pi. All right? We're going to leave out this e to the I 2 pi p jh outside. E to the I something minus e to the negative I, the same guy, is 2i sine that guy, all right? 2 pi ph. 2i sine 2 pi ph plus what do we have is epsilon over h squared. E to the ix plus e to the minus ix is cosine, right? That's 2 cosine 2 pi ph minus 2, right? Again, what we use here is e to the ix plus e to the negative ix. This is 2 cosine x e to the ix minus e to the negative ix. That's 2i sine x. Okay. So what we had above showed that this lambda p is actually equal to, so this is going to be lambda p times v at j, alright, v at j. So lambda p is negative a over 2h e 2I sine 2 pi ph plus epsilon over h squared 2 cosine 2 pi ph minus 2. To simplify this a little bit, we're going to get this is 2 epsilon over h squared, negative 2, alright, now plus 2 epsilon over h squared cosine x minus a over 2h, 2a over 2h, so that 2 goes away, the a over h, I sine x. Here x is nothing but 2 pi ph, okay, 2 pi ph. Recall that what we need is lambda, the eigenvalue of that matrix A times theta t in the f-forward Euler stability region, right, which is that disk. Okay, so we need to look at theta t times that lambda p, which is negative 2 epsilon theta t over h squared plus 2 epsilon theta t over h squared cosine x minus I a theta t over h sine x. Okay, and if you look at this guy, so if you look at this guy, this is in the form of a cosine x plus I b sine x. Okay, and the first part is basically just that shape. This shape shifted, right? Shifted by the by that amount. Shift to the right by negative number, which like shift to the left. So as the x changes, right? So this is as we were discussing the forward Euler stability region, you need to be able to visualize this region. So what is a cosine x plus I b sine x? If a is equal to b, this is like cosine x plus I sine x as x goes around, as x goes through all the values, is just a unit disk. Okay, unit disk. That's a point. Here is a point, cosine x and sine x, right? So as x, this makes this circle. So when a is not equal to b, this becomes the ellipse, right? Which is you're going to get, if a is large and b is small, then here is b. I mean b can be negative, so it's b absolute value. Here is negative b absolute value. Here is a absolute value. Here is negative a absolute value. All right. That's this shape. So, and then the shift is to the left by 2 epsilon theta t over h squared. Okay. Which is for the lambda theta t lambda p, and this is like you shift to the left, right? Shift to the left, which is negative 2 epsilon theta t, that first number, over h squared. Okay, and that a is the same guy, so it will reach exactly in the origin and something like that. This value is nothing but zb, right? What is zb? That is a delta t over h. So this is a delta t over h. This is negative a delta t over h, okay? So we want to make sure this is contained in the f-forward Euler solidity region, which is this guy. He's negative 1, he's negative 2, right? In particular, we need that negative 2 epsilon delta t over h squared. That's the center of that ellipse. You move to this point, this would be negative 4, right? Negative 4. This should be larger than or equal to negative 2. Okay? We are saying this point should not be to the left of negative 2. Otherwise, the left end of the ellipse will be outside of the forward Euler stability region. Okay? For example, for the Lex Wendroff, we know that epsilon is 1/2 a squared delta t. Okay? So what this is that we need negative 4 epsilon is 1/2 a squared delta t times delta t over h squared larger than or equal to negative 2, which is to say 4 divided by 2 cancel with 2 on the right hand side, which is to say a squared delta t squared over h squared is less than or equal to 1. All right, that's a condition we wrote down already. So that's a delta t over h, absolute value is less than or equal to 1. So once you fix h, you need a smaller delta t. That makes this inequality hold. Okay, otherwise your skin is not stable. So next we're going to visualize this delta t times lambda p. Okay, this can easily be coded up. You just calculate that formula that we just derived, and by going through all the x, all right, between 0 and 2 pi. We're going to just take what we have in the book, page 208 from the book. So here the h is 1/50, all right, and the delta t is 0.8. A is 1, delta t is 0.8 times h. So this way that a delta t over h is equal to 0.8. Okay. So in particular for the Lex Wendroff, we have this 1/2 a squared delta t, right? So that's going to be 1/2 times 1 times delta t, which is 0.8 times 1/50. So what is that? That's 0.4 divided by 50, which is 0.008. That's why this 0.008 corresponds to Lex Wendroff, and the Lex Friedrichs is h squared over 2 delta t, right? So what is this? This is 1/50 squared divided by 2 delta t, which is 0.8, divided by 1/50. So we can cancel this, and with that, so we're going to get 1 divided by 80, right, which is 0.0125. And that's why this is Lex Friedrichs. So when epsilon is 0, we get the skin 1, right? That's just a skin 1. skin 1. Forward order in time, central in space. As we talked about in about 2 videos ago, these are that matrix is asymmetric, so its eigenvalues are purely imaginary. So that's not going to be stable because it's not included in the forward order stability region. And as you see, we gradually increase epsilon, right? When epsilon is 0.001, it starts to have a little bit of overlap. All right, but of course, that's still part that's outside of the region, so that's not good. And when continue increasing to 0.005, it's just a little bit outside, all right, a little bit outside. And when finally we are at the Wendroff location, 0.008, we see it's completely inside. All right, here's -2. And when it goes above, goes larger to the Friedrichs, that's again more dissipative with larger epsilon, is still within the region. Okay, it's still within the forward Euler stability region for the ODE. So that's still stable. So that's stable, not stable. Right, not stable, not stable. When you continue raising that, then that's what we talked about in the last slide. This is going to be stay outside of that -2, okay? So it will be not stable again. So what you can practice is that you can just plot this delta t times lambda p, right? And you vary epsilon, right? I vary epsilon. In particular, for this particular example, when epsilon is between 0.008 and 0.0125, the skin will be stable. You can vary that epsilon and plot that region. You'll see as the epsilon varies, this region will change. Okay.